To begin this lesson, I want to go ahead and try getting you guys used to the idea of factoring to help us understand the graph of a polynomial. So anytime you can factor a polynomial, you can find all of the x-intercepts. So factoring is a really quick and easy way to match a picture to its graph. So one thing I know about letter A is it's going to be a smiley face because it is quadratic and it's positive. And this does factor pretty easily into x plus 4 and x plus 1. So the x-intercepts are going to be at -4 and -1. So we're looking for a smiley face that has those intercepts, and it looks like it's going to be C, graph C. If I jump to letter B, when I see 4 terms, one of the quickest things you can do, and sometimes it works, sometimes it doesn't, but it doesn't hurt to try, is to group it. And then we're going to factor out the GCF from each parenthesis and see what happens. So I know I can pull out x squared, and that leaves me with x minus 2. I can also pull out -1, and that leaves me with x minus 2. So this particular grouping worked because if you look at your parentheses, they match up, which is exactly what we want to happen. So I can pair up my x squared and my -1. Keep my x minus 2, and I can factor this even a little further because this is a difference of squares. So I can actually turn this into x minus 1, x plus 1, times x minus 2, and all of that still equals 0. So this is going to be a cubic, a positive cubic, so it's going to look something like that. And it's going to have 3 x-intercepts, 1, -1, and 2. So we want to look for the graph of the cubic that's doing that, and it looks like it's going to be graph F. There's your -1, your 1, and your 2. So we're going to go ahead and match B to F. So when I look at letter C, I see right away that there's a GCF. So I'm going to begin by factoring out an x, leaving me with x squared plus x minus 2. Then I look at this quadratic and I just ask myself, could that quadratic factor? And it can into x minus 1 and x plus 2. So this is going to be a cubic function. It's still going to look something like that, but it's going to have 3 x-intercepts, 1 at 0, 1 at 1, and 1 at -2. So if you try to look between letters A and E, since those are both cubic, it looks like it's going to be letter E. You can double check, but we have an x-intercept at 0, 1, and -2. So E goes with C. Alright, so we'll give D a shot. We see that there's a GCF of x, so we'll factor that out real quick. And then we have ourselves a difference of squares, so we can factor that down. And so I have 3 x-intercepts, 1 at 0, 1 and -1, and that's going to go with graph A. Now for graph E, we might not know how to graph that, or how to factor that, because it has x to the 4th, and we haven't learned how to factor things that are really higher than squared unless they have a GCF, and there is no GCF for letter E. But the good news is it is in standard form, and when something's in standard form, the last number is the y-intercept. So I know that E and F are both going to be basically smiley faces, but I know the x-intercept for E has to be 4, or excuse me, the y-intercept for E has to be 4. So between graph B and D, this one has to go with D, because D has a y-intercept at 4, and B doesn't. So I know E goes with D, so consequently, little f would have to go with graph B. So the whole purpose to these notes is to get us using different ways to factor so that we can really break down a polynomial and know how its graph behaves. So I just kind of have that rule reiterated. Factoring allows us to find zeros, aka x-intercepts, and then we can understand the shape of our graph very quickly. So just to review, there's factoring methods that we've already been using. And one of them is just factoring out the GCF, and that should always be your first step in any problem. You always want to make sure if there's a GCF, we factor that out first, because chances are it's going to make your life a lot easier. So if you look at the example below, between 4 and 18, they share a factor of 2. R squared and R squared share a factor of R squared, and K cubed and K share a factor of K. So my GCF is 2R squared K, and if I factor that out, I'm left with 2K squared minus 9, and that's it. And then we've been using the X method up until this point, but again, first step is factor out the GCF. So we're going to factor out X, leaving us with X squared minus 4X minus 5. And then we're looking for numbers that multiply to make -5 and add to make -4. And those would of course be -5 and +1. So then we can simply write X minus 5 and X plus 1, since the leading coefficient was 1. So that's factored very quickly. Again, pulling out the GCF, so we can pull out it looks like a 2K actually, leaving us with 2K squared plus 7K plus 3. We're still going to use our X method, but because we have a 2 in front of our K squared, we're going to have to use grouping. So I would multiply 2 and 3 together to get 6. 7 goes downstairs, and then I'm trying to find my magic numbers. So it looks like 6 and 1 will do the trick. So I'll just kind of ignore this 2K for right now. I'm going to focus on the quadratic part, and we're going to rewrite it as 2K squared plus 6K plus K plus 3. We're going to group it up, pull out the GCF of 2K. You always have a GCF. If you don't see one, it's 1. So this is going to factor into 2K plus 1 times K plus 3. And we just don't want to forget our GCF that was out front the entire time. We just don't keep copying it. So that is completely factored. And then special types of factoring problems, difference of squares, very, very quick and simple. If you see a subtraction problem with 2 squares, you can actually factor using the difference of squares. It's up to you. We can pull out the GCF right now if we want, or we can factor it as is, because these are perfect squares. Doesn't matter, you're going to get the same answer overall. So I'm going to actually do it both ways. I'm going to show you how to make sure that you can see, oh, they both work out the same. So the square root of 64 is 8. Half of m to the 4th basically is m squared. And then square root of 36 is 6. So we're going to have an 8m squared minus 6 and an 8m squared plus 6. We never want to have a GCF in either parenthesis. So between 8 and 6, I recognize a GCF of 2. Same thing here, so I'm going to write 2. And then what I can actually do is, remember, this is all just multiplication. Order doesn't matter. So I can multiply the 2's together and put them out front, and then put my parentheses in my answer. So this is completely factored. Even though 4m squared is a square, 3 is not, so we don't have any difference of squares remaining in the problem. So that's like version A, if you want to do the problem that way. Let's say you're a GCF person, you pull out the GCF, which in this case would be 4. So if we divide 64 by 4, we get 16 m to the 4th minus 9. And then we take the square root of 16m to the 4th, which is 4m squared, and the square root of 9, which is 3. And then we'll just have a 4m squared plus 3. So we get the same answer. It doesn't matter which way you do it. If you take the GCF out first or last, doesn't matter, as long as at some point you factor out a GCF. So this is classified as review. We have been doing this for quite a while. Now we're going to make it a little bit harder. So how do you deal with situations that don't have a GCF, but your exponents go above 2? So for example, if you have an x to the 4th, how do you handle that if there's no GCF? We have a couple tricks up our sleeves. We're going to learn about the sum and difference of cubes and how those formulas can be applied to a problem. So we have that trick up our sleeves. We still can utilize grouping. It might not work for us. It's not bad to try it, but you may not get anywhere from it. You don't know unless you try. And then I'm going to teach you another method called quadratic form. So within all your tricks to factoring, you have the X method with grouping, GCF. We're going to add on 3 different tricks to that. Just makes you more skilled in factoring. I have a little note here because we're going to see this happen in one of our examples, that a polynomial could potentially not group, but yet it still could be factorable. So if you try grouping and you don't get anywhere, it doesn't mean, oh, it's not factorable. It just means you're going to have to use a different approach. So in my next video, I will go ahead and begin by showing you guys how to use the sum and difference of cube formulas and talk a little bit about cubes.